Oh no, I'm so sorry.
Oh, Lyra, it's all right, really. Don't worry.
Imagine, for just a second, that our Earth's atmosphere isn't just empty space or thin air. Instead, picture it as a massive, intricate, fully interconnected 3D machine. It's literally like a giant puzzle, where every single moving cog and gear is deeply attached to the next. If you shift just one tiny piece, well, the ripple effect ends up changing the entire system. Welcome to this explainer. Today, we're going to break down the core elements of weather and climate so we can understand exactly how this fascinating atmospheric shell surrounding our planet actually works.
So here's the 6-part blueprint for the atmospheric machine we're building today. We'll start with weather versus climate, move on to temperature and atmospheric pressure, explore the dynamics of wind, map out humidity and precipitation, examine cloud types and visibility, and finally, we'll bring the whole shebang together with the atmospheric domino effect.
All right, let's start right at the foundation with Section 1, Weather versus Climate, the foundation of the atmosphere.
Now, people often use these two terms interchangeably, right? But they actually operate on vastly different scales. It really all comes down to the time frame. Weather is your immediate reality. It's what is happening right outside your window at this very second, whether it's pouring rain right now or if the sun's going to shine brightly tomorrow. But climate, that is the massive, long-term average of those daily weather patterns. Actually, it's typically measured over a sweeping 30-year period. It's a huge gap in time. But what's truly fascinating is that both your daily weather and the multi-decade climate are driven by the exact same mechanical elements.
Moving right along to Section 2, Temperature and Atmospheric Pressure, the engine's primary drivers.
Let's look at what actually powers this machine. Notice how solar radiation hits the Earth perfectly head-on at the equator? That direct angle creates immense, intense heat. You see, temperature isn't just about feeling hot or cold. It's completely dictated by this raw energy we receive from the sun. But as you travel away from the equator and head toward the poles, that energy spreads out and the temperature drops rapidly. And here's the kicker. This immense heat doesn't just warm us up. It ultimately controls both the pressure of the air and the moisture floating in it worldwide.
This dynamic creates a really fascinating relationship. We measure temperature with a thermometer, of course, and that heat directly dictates the literal pressure of the air. And right next to that is atmospheric pressure, which we measure with a barometer. To put it simply, atmospheric pressure is the physical, literal weight of the air continuously pushing down on us from above. It's heavy. But because air gets thinner the higher you climb, that heavy weight drops off extremely fast as you gain altitude.
So let's see how these two drivers create a perfect mechanical cycle. When the sun heats the air, that air becomes super light and it rises, leaving behind a low pressure zone right near the ground. As that hot air climbs higher into the sky, it cools down and forms clouds. Once that air becomes cool and heavy enough, gravity takes over. It begins to sink right back down to Earth, creating a high-pressure zone that essentially pushes away clouds and leaves us with completely clear, calm weather. It operates just like a continuous, invisible domino effect.
And that brings us to Section 3, the dynamics of wind, the atmosphere in motion. So, we just learned that air pressure moves vertically, up and down. But that begs the question, why does wind constantly blow horizontally across the map? Well, the answer lies in a simple physical rule. Air desperately wants to rush from a high-pressure zone to a low-pressure zone. The difference between those two zones generates a distinct physical push, and scientists call this the pressure gradient force. The larger the difference in pressure between two areas, the harder this mechanical push becomes, and the faster the wind will rush across the map. This is the exact literal force that drives air from one corner of the globe to another.
You can kind of think of these winds as the giant conveyor belts of our atmospheric machine, and they come in a few different classifications. We have permanent winds, like the trade winds and westerlies, that blow consistently all year round. Then we have seasonal winds. Take the monsoon, for example. It's not just a wind, it's the literal lifeblood of India's entire agricultural system. We also have very specific local winds, like the blistering hot loo that sweeps across northern India in the summer. To track these conveyor belts, meteorologists use an anemometer to measure wind speed and a wind vane to tell us its exact direction. Let's explore what those winds are carrying in Section 4, Humidity and Precipitation Patterns, Moving Moisture.
So, what happens when these conveyor belts carry water vapor? To truly understand moisture, we have to grasp two completely different types of humidity. First up is absolute humidity. I want you to imagine a 3D block of the atmosphere, just a floating box of air. Absolute humidity is the literal, precise physical weight of the water vapor physically floating inside that specific block.
But relative humidity, that is entirely different. It's a ratio. Think of coastal cities like Mumbai or Chennai. When you're there and it feels incredibly sticky and sweaty, it's not just the heat. It's because the relative humidity ratio in those areas is maxing out. That means the air is absolutely stuffed to the brim with moisture compared to the absolute maximum capacity it could possibly hold at that specific temperature.
So, what happens when this completely moisture-packed air is forced upwards? Say, it blows over a dense forest or hits the side of a massive mountain. Well, it cools and condenses. Those invisible water vapors turn into literal liquid drops or ice particles. Eventually, these clusters become entirely too heavy for the air to support, and yep, gravity takes over again. They fall back to Earth as precipitation, which could be rain, snow, hail, or sleet. And we measure this exact output using a remarkably simple but effective tool, the rain gauge.
Which smoothly leads us into Section 5, Cloud Types and Visibility, the sky's thermal blanket.
Obviously, before that precipitation actually falls, we get clouds. But what exactly are they? At their core, clouds are really just floating clusters of condensed water and ice crystals. Scientists group them by their height and shape. You've got the high, wispy cirrus clouds, the fluffy cumulus ones, the thick, layered stratus clouds, and finally, the dark, heavy, rain-bearing nimbus clouds. But classifying them is just the beginning. The most fascinating part about clouds is their vital function for our planet. Clouds actually act as nature's thermal blanket. During the day, they reflect a significant amount of the sun's harsh solar radiation right back out into space, which keeps the Earth from totally overheating. But at night, they do the exact reverse. They trap the heat that the Earth is trying to emit, keeping us nice and warm. So the absolute crucial takeaway here is that clouds heavily regulate our temperatures. That is exactly why on heavily overcast days, you'll notice there's very little difference in temperature between the daytime and the nighttime.
Now, down near the ground, moisture and suspended particles play another critical role. They completely dictate atmospheric visibility. Things like fog, haze, huge dust storms, and smoke drastically reduce how far we can physically see. And while that might just seem like a minor inconvenience in the grand scheme of climate studies, it is absolutely crucial for our daily lives. Tracking these low-hanging atmospheric particles is vital for the safety of aviation and marine transport. Ships and planes completely rely on clear visibility to operate safely.
And finally, Section 6, the atmospheric domino effect, the delicate balance. Let's bring all these moving cogs together.
We've looked at the individual pieces of the puzzle. Now let's see the grand atmospheric interaction at play. When you look at the stark contrast between miles of bone-dry, barren deserts and vibrant, dense, lush rainforests, you are actually looking at the exact same atmospheric machine at work. The only difference? The specific, deeply intertwined combination of the elements we just discussed. It's the real-time interaction of temperature, air pressure, wind, and humidity that determines the physical reality of absolutely any region on Earth.
The big so what that you should take away from this is that no single element ever works in isolation. Temperature, wind, and pressure are deeply and beautifully entangled. Our Earth's climate balance is incredibly delicate. Every single gust of wind, every tiny drop in atmospheric pressure, and every rising degree of temperature absolutely relies on the others to keep the global system functioning smoothly. Which brings us to a final, pretty profound thought. Knowing that our atmosphere is a giant, perfectly balanced domino setup, if just one element, say a single wind pattern or our global temperature, changes permanently, how will this massive atmospheric domino effect alter our entire map? It's a fragile, deeply fascinating world out there, and understanding these fundamental elements is the very first step in protecting it. Thank you so much for joining me for this explainer, and keep looking up.